this one becomes my favorite number for a very personal reason. And the reason I absolutely love it is that in the year 2025, I will turn 45. And so for a brief moment, I will turn the exact square root of the then current year. I mean, what a birthday party that's going to be. It's going to go off.
So I'm not calling it the Parker Square.
Obviously, blue and black.
It is totally blue and black.
Ladies and gentlemen, I have really excelled myself.
Pokemon Go has only been out for a few days.
It's going to be a tough play. The Cubs win the World Series!
A real football has light hexagons and dark pentagons. I don't know if I brought this up earlier, Hannah, but it's 80% accurate.
The first ever glimpse of a black hole in space.
There it is! That's the sign!
Tropical rainforest to the edge of time itself.
And made it over 4 million% better.
A Willy Wonka experience in Glasgow.
I am going to work one of these out by hand.
I'm going to try and calculate pi by hand again.
By hand. By hand. A record amount of pi by hand. It's 2025, 10 years after that number file video, and we are finally here. Of course, I had to make a video to celebrate, although if you know the original video, you realize this is not the party hat I should be wearing.
You thought about what you're going to do for your birthday? Or?
Oh my goodness, I don't know. I've still got I got a decade of planning to go, and it'll be square themed. All the food will be square shaped, and not cubes, not cuboids. People are thinking square cake. No, it's infinitely thin slices of square cake. Now, for the record, I haven't had my birthday yet. It is 2025, but my birthday is actually dangerously close to the end of the year. It's like practically Christmas, which is annoying for its separate birthday-related reasons. However, I don't want to do a video right at the end of the year when I should really be celebrating it in the middle of the year. And this is the year, 2025. It's a square number year, and I will turn the exact square root of 2025. I will turn 45 later this year, as will anyone who, like me, was born in 1980. Now, I stand by all the maths in the original video from 10 years ago. It's maths, it's all still correct. And in that, I talked about other years where you can turn a root of a future year in that year. And I talked a lot about the year 2184. You can check that out at your own leisure. Hello from the past. This is how we used to live. Here are, I mean, these are, we used to use dead trees to store information. And although maybe all of anything digital will be destroyed and people have no idea about YouTube, but they'll still have these books. We don't know. So when I sat down to make a video about 2025, which I knew I absolutely had to do, I suddenly realized there's some more maths. And I didn't notice this because I was making it all about me and my birthday. But there's another fact about 2025 that everyone can enjoy, and it's possibly more impressive. I was so focused on the fact that 2025 is a square number of 45, I didn't notice that 45 is a triangle number of 9. And so you actually start with 9, and then you triangle it, and then you square it. And while square numbers are wonderful, big fan, triangle numbers, they're pretty cool. For example, did you realize bowling is actually named after a triangle number? It's 10 pins because that's a triangle shape. 1 plus 2 plus 3 plus 4 is 10. And triangle numbers are just the sum of consecutive numbers starting at 1. So it's not because 10's a nice round number, it's because it's a triangle number. That does mean you could do any other triangle number. And we care about the 9th triangle number, which actually means if you were to ask a bowling alley very, very nicely, it's technically possible to go 45 pin bowling. Thankfully, we were at Murrayfield Indoor Sports Club in Edinburgh, and they were very accommodating. This is Graham, absolute champ, crawling around to arrange the first ever setup for 45 pin bowling. Look at it. It looks like there's some kind of glitch. Isn't that amazing? And if you take a close look at the back row, there are indeed 9 pins side by side, and it turns out that's the maximum number of standard bowling pins that can fit on a standard width lane. This is the maximum of triangle pin bowling. Come on! No! No! Could have been the first ever. It was a Parker strike. Unbelievable. 1 pin. So there you have it, the first ever bowl of 45 pin bowling scored 44, and the first, and I suspect only ever frame, was a spare. And I can't think of a better way to celebrate the fact that 2025 is the square number of a triangle number. The main new fact that I only realized this year is that if you square a triangle number, which means you're summing the numbers from 1 through to n and then squaring the total, that always gives you exactly the same result as if instead you took the same numbers from 1 through n, cubed them all first, and then summed them together. That's true for all triangle numbers, and because this is a very rare year that's the square of a triangle number, it's true of 2025. And now to explain why there are piles of acrylic next to me. You see, I was talking to the people at Jane Street. They're a financial company who sponsor a lot of my videos, including this one, bonus puzzle at the end. And I pitched the idea of doing an installation in one of their offices based on the interesting number facts around 2025. I thought that could be a lot of fun. We bounced this around between some people who work at Jane Street, and someone named Andy Niedermeyer suggested we take the fun fact about 2025 being the sums of cubes, and we use the related fact that turns it into what's called the Partridge puzzle, and that's what we install in the Jane Street office. Hear me out. If the first 9 cube numbers add to 2025, we could take all of those cubes and split them into layers. So the 9 by 9 by 9 cube could be 9 layers that are each 9 by 9 squares. And the 8 cube could be 8 layers that are all 8 by 8 squares. And then all the way down, and that's what I've got made out of acrylic here. There's 9 layers. Now, we could have made them all thick enough. This was an actual physical cube. That wasn't necessary, so we didn't do that. But there are 9 squares that are all 9 by 9. We go all the way down to 2 squares that on the same scale are 2 by 2, and then we have a single 1 by 1. That's technically the cube, but of course it's a little bit more flat. Now, if you were to add up all of these squares, they should still sum to 2025. But because 2025 is a square number, if you had one giant square, that's 45 by 45, it will have the same surface area as all of these smaller squares. And the reason the person who first popularized this relationship, someone named Robert Wainwright, called it the Partridge problem is because it's a bit like the 12 days of Christmas. But now there are 9 squares of 9 and then all the way down. You can imagine how that goes. It's once again a Christmas song busting in on my birthday.
1, 2, 3. On the 9th cube of squares, my secrets get to me. 9 squares of 9, 8 squares of 8, 7 squares of 7, 6 squares of 6, 5 squares of 5, 4, 3 squares of 3, 2 squares of 2, and one sum of 3. All sometimes squared equivalent.
Music aside, we wanted to physically make one of these, so we put together a massive one, got it manufactured and installed in the Jane Street office in New York. And thankfully, I was recently able to visit it. And I was joined by Jane Streeter Sawyer Tabany. We had a bit of a play, and first of all, we thought we would show every side length is 45 as a triangle number by stacking one of each square from 1 to 9 to show they add to 45, which was fun, and then we set about playing with the pieces. We quickly realized it's quite difficult to do,
And you might be thinking, well, hang on, just because the numbers are the same, the surface area of the square and the pieces is 2025, that doesn't necessarily mean there is a solution. I mean, that fact is necessary, but it's not sufficient.
And that's true in general.
Yep, that's true for any n. It's kind of a surprising fact, but yeah.
And is this arrangement true for any n?
This arrangement does not exist for every n. That's a really interesting question.
It turns out, yes, it only works for the case n equals 8 and upwards. And Sawyer and I had a closer look at the case for n equals 3 to give an example on a smaller, easier scale of why sometimes it can be impossible.
Yeah, so you'd have a 3 by 3.
Yeah, which I guess
is one of those.
One of these.
Let's just put that in the middle. So that's that.
Yep.
And in theory, these would cover it.
Yep, they do in fact equal in
area.
They
do, yeah, but you have to double cover the center.
Right.
And you get that.
And you miss that.
And that double cover should be there.
Yep.
But there's no other way to arrange those.
Yep, exactly.
Oh, but now. Okay, I mean this is it's a lot of fun to try and solve, but incredibly difficult. I think I used the 1 up too early, and now I've got these stacks. I mean, I probably could get away with all 9s up the side here, but these towers of 6 and 5, I can't get out of that because I've already used up my 2. Oh, there's not enough.
It turns out it's very difficult for humans because when you're trying to put the last few pieces in, whether or not they fit is kind of predetermined by decisions you made ages ago, but you don't know if those decisions were right or wrong until you have to put a lot more effort in to fit the remaining ones. So you're kind of at the mercy of how lucky you were putting in the earlier pieces, but with no way to know in advance whether or not you got it right. And we should just have a moment's reflection for all of Beck Hill's free time that was consumed by this puzzle. Beck was sharing a flat with me. We're at the Edinburgh Festival Fringe, and despite my warning, she got a bit addicted to the puzzle. And it's so much fun, but it's so hard. I'm sorry, Beck. That said, if like Beck Hill, you would like to waste vast chunks of your free time and you can't be bothered cutting out squares of cardboard, Matt Scroggs has made an interactive version of this which we've put online, so feel free to give it a go. But you probably shouldn't.
So while it is fun to do as a human, oh my goodness, the odds of finding a solution are so small. And the thing is, there are a lot of ways to do this. There's over 1 million possible solutions. There's 1,730,280 ways these can fit into that. And the reason I know that is because we wrote some code to find them all. Here they are.
I have never solved it.
Yes.
Solo, yeah, that's right. I have never solved it, the entire puzzle.
No, nor have I. I wrote some code if we want to find a solution. Let's just bring one up.
Yeah, that sounds smart. I like that.
Behold, many, many solutions. My good friend Matthew Scroggs put together some code to find every single possible solution. I then wrote some code to categorize the solution. And first up, we have the 352,072 solutions, which have an L shape of 9 by 9 squares. So these are just the solutions for n equals 8, but with a big L of 9s around the edge. I don't find these very exciting. Better are the 1,303,584 solutions which just have a single stack, a column of 9s. I guess we call those an I of 9s. And the vast majority of the solutions seems to have a I like this of 9. So I guess a little pro tip there if you're going from scratch, although that's technically cheating. The point is, I think these are more mixed up than the L's. Even better, though, are the 74,624 solutions with no neat lined up stack of 9s anywhere. I think these are the best. Look at them, they're all over the place. And it could be argued these are the best solutions because they make better use of the 9s.
For the record, in the code, the 1,730,280 solutions includes all rotations, 4 of them, and the 2 reflections, which normally we would get rid of. And if you divide by 8, there are 216,285 unique solutions, but we've left them in because the act of solving it, you're solving one specific arrangement. So if I put some shapes here, I'm only working, they're not also equivalently here and here. I'm only working towards one set solution. So that's why I stand by my over 1 million claim.
So my code has taken this solution to be different to that solution, which is different to this one, and this one, which I kind of stand by, like I said, because when you're building it, they are different. Also, it's a slippery slope. If we count this one, do we count this one? What about that one? All the L shapes, you could just rotate the middle n equals 8 case. Or what about within that, see those three there? We'll spin them around. There we go. Is that a whole new solution? Who knows? You could try to slim them down. I maintain there are over 1.7 million solutions. Because this is such a hard puzzle to do by hand, I made the prediction that when we installed it at Jane Street, staff members would go away and just write code to find a solution and come back and put it in. And sure enough, that's what happened. James did it, and he was kind enough to come and explain how his code worked. You're at work at Jane Street.
Uh-huh.
You see this puzzle.
Uh-huh.
Did you try and do it physically?
Yes.
And did you find anything?
No.
Right. And so then you stormed off and got some old code from high school.
Uh-huh.
And that found a solution.
Yeah.
Okay. So what did the old code do?
The old code solved a more general set of problems of polycube packings. So you can think of like Tetris in 3D puzzles.
Yep. Like the Soma Cube kind of.
Yeah, like the Soma Cube. While solving this, I learned that there were lots of dead ends. You can like fill out half the board, and then like the other half just has like no solution. And that means like my solver is like doesn't like skip anything. It like tries every option before like
goes every branch until it realizes there's no solutions at the very end. Right.
Yeah. I ran it overnight at work. And I only got one solution.
Oh wow.
Yeah. So like after like hours of computation time, I only got one solution, which is like just shows how like unoptimized the solver is for this particular situation.
Yep. But I found one.
Yeah, I found one. That was nice.
And did you build it out of this?
Yes, I did. Okay, so while I was home, I like rewrote a different solver from scratch.
Right from scratch.
that is like much more optimized for this
specific problem.
Yeah.
Right.
And I like really tried to optimize it too because I thought it would like still take like forever. Bottom line, it finished in like a couple seconds. Like it found a solution in like a few seconds.
Boom,
like
solution.
Yeah, like almost instantly. So the next day I came to work and I like put a like constructed that solution. So let's say we're in like this state, I guess.
Okay.
Yeah.
This
is good enough.
Good.
So what we do in a partially solved state is that we scan like in row major order from like the bottom. I guess it doesn't really matter. So we scan
as long as
this
you're systematic.
way, like in some direction.
Yep.
And eventually we'll find an empty cell. So in this case, this happens to be the first empty cell, and we just recursively descend on that. So we try this one. Now recursively descend. Now this is the first free cell. You can fill this in.
Yep.
And now if we scan again,
this
we can see this one.
And nothing that's left is going to fit there.
Yeah.
And so it backtracks up.
Yeah, backtracks. So nothing fits here. So backtrack again.
To there.
Fill this one in. This is the next empty cell, but there's only one choice. This
and
is
then
the next
that one
empty
there.
cell. Yeah.
And then you hit the very end and you're done.
Yeah.
The only person I know of who has solved this, the 45 squared case, by hand as a human is Andy. And Andy's obsessed with this bit of maths. Andy's the person who had the idea to turn this into the puzzle when we were discussing things about 2025. So, does that count? I guess so. Well done, Andy. You be the judge.
Hi, Matt. This is Andy. I'm a trader at Jane Street. I'm the person who came up with the puzzle with the partridge tiling. Spoiler alert, the sum of cubes is a square is the message of the puzzle. And so the goal was how can I kind of like hide that in this in these grids. I think one thing that's really cool about this kind of partridge tiling style of puzzle is that it's really not guaranteed to exist. If you swap out the pieces for different shapes, like say triangles or trapezoids, then it might be the case that you only start seeing valid tilings at different multiples. Like maybe for certain shapes you need a lot more pieces before you can find any solutions, or maybe you need fewer pieces. And I think that kind of unpredictability is pretty cool.
And finally, thank you so much to Jane Street for also sponsoring this video, among many of my videos. And the reason they're sponsoring this one is I'd like to share another puzzle with you, which I will link to the URL in the description below.
The puzzle is basically this neural network PyTorch file that you download and interrogate to try and work out what the logic is behind it. And that's because while neural networks can be very powerful despite being completely opaque, Jane Street likes to know what's actually going on inside the box, so you can see if you've got the skills to dissect this neural network. You see, Jane Street are a research-driven trading firm, and they believe that deep learning like this is the future of quantitative trading. And so they've got a machine learning team who build neural networks that help drive their trading strategies, and the same team works on the infrastructure that makes the training and inference possible. And that same machine learning team, which if you're curious about joining, I'll have a link in the description, also put together this NeuroNet puzzle. If you think you've solved it, please do email Jane Street and let them know.
And if you solve the puzzle, you can be one of only currently 19 people who've done that. Well done to those 19 people. And if you're thinking, hang on a second, I thought Jane Street were a financial company. Why have they got, well, seemingly a whole department dedicated to puzzles? Well, I asked Sawyer the same thing.
We like puzzles here. I think there's just sort of a correlation between being a good Jane Street employee and like enjoying and being good at solving puzzles. And so in a way, a puzzle is a bit of a simulation of what it's like to be a Jane Streeter, right? We're trying to solve problems that other people haven't solved. We're trying to like write new code. And then we also get to like have puzzles on our website, and maybe people enjoy visiting our website and learning about our work, and we have like these puzzles that people can interact with. There's a bit of a community there, and it is a little bit of a, hey, if you like this puzzle, maybe you'd like to work at Jane Street.
To find out more about puzzles and indeed machine learning jobs at Jane Street, I'll put a link in the description below. Thank you so much to Jane Street for sponsoring this video.
And thanks to the a cappella group Out of the Blue, who recorded our mass version of the 12 Days of Christmas. Now the reason I'm filming in a bit of a weird location is I'm actually at the Edinburgh Festival Fringe doing 27 shows in 27 days. Out of the Blue are up. They are also doing the entire run.
Remember, this is going out to the Matt community. 1, 2, 3. On the 9th Cube of Square, as my secrets came to me. 9 squares of 9, 8 squares of 8, 7 squares of 7, 6 squares of 6, so 5.